Hi there, Physics 20 class. In this U Try 1, we're going to look at gravity fields. Now keep in mind, this is a concept that we learned back in Physics 20, but it's good practice because it's going to deal with electric fields, very similarities. So I'll share the screen here and we'll look at it. So calculate the gravitational field strength at the location of a 70-kilogram astronaut that is 2.0 radius of the Earth from Earth's center. Use the data from table 4.1 on page 218. Surprisingly enough, you can find the same data on your formula sheet that are given to you on your diploma. And in there, we will need the Earth's mass and the Earth's radius. Now keep in mind we have to multiply by 2. So do stop the video now and try the problem. Once you come up with a solution, please press play and see if you came up with the same thing. I'm going to be using GRASP, keep that in mind. G for given, R for required, A for analysis, S for solution, and P for paraphrase. Do pause the video now and complete the question. So with this in fact, you're going to be realizing under a given, we were given a mass that is 70 kilograms. We're given the mass of Earth, which is on page 218 or in your data booklet, 5.97 times 10 to the 24. So for a radius, which is really the distance from the Earth's center, you have to times it by 2. So 6.38 times 10 to the 6 times that by 2. So I've included a diagram here to get a better understanding of the problem. And in there, you're going to be realizing there's an astronaut and there's the Earth. It's double the amount, and that's where that's coming from. So under the required, we are looking for lowercase g, and it is a vector quantity, so we're going to have direction at it in the end. Under the analysis and solution, you can put those in together. Just make sure the significant digits are correct at the end. So use the equation g equals capital G m source over r squared. And if you do that, that is your constant, capital G, 6.67 times 10 to the negative 11, times it by 5.97 times 10 to the 24, that's the mass of Earth, then the radius, which is 2 times the amount, as I said earlier, and then square it. You should get 2.4 newtons per kilogram. And here's the important bit, towards Earth's center. If it wasn't towards Earth's center, then he would be just floating away in space, probably to the next planet, wherever the gravity is stronger. So this is an essential bit to always include the vector quantity. Now keep in mind, why didn't we use the mass of the astronaut? Because the mass of the astronaut is not applying to this gravity. So keep that in mind, we had to use the mass of the Earth to actually get a better understanding. It didn't matter how big the astronaut was, unless he's heavier than Earth, but unfortunately, it's not going to happen. So if there's any other questions on this you try, please don't hesitate to let me know. Have a good day.